Welcome to this comprehensive guide on robotics, interview questions focusing on automation and artificial intelligence integration. Robotics has become a rapidly growing field that combines mechanical engineering, electrical engineering, computer science, and artificial intelligence. Whether you are preparing for an entry-level position or an advanced robotics engineering role, understanding the fundamental concepts is crucial for success. Today, we will cover the core focus areas that are essential for any robotics interview, including control systems, sensors and actuators, artificial intelligence integration, and robotic automation. These topics form the foundation of modern robotics and are frequently discussed in technical interviews across the industry. Control systems are the brain of any robotic system, determining how robots respond to inputs and execute tasks. The three-tier architecture is a fundamental concept in robotics that divides the control system into three distinct layers. The planning layer handles high-level decision-making and path planning, determining what the robot should do. The executive layer manages the coordination between different subsystems and translates high-level commands into specific actions. The behavioral layer deals with real-time responses and immediate reactions to environmental changes. Key components include sensors that provide environmental feedback to understand the robot's surroundings, actuators that execute control commands to create movement, controllers that process information and coordinate actions, and feedback loops that ensure system stability and accuracy. This architecture allows robots to operate autonomously while maintaining safety and precision. Sensors are the eyes and ears of robotic systems, providing crucial information about the environment and the robot's own state. There are four primary sensor categories that every robotics engineer should understand. Position and motion sensors include encoders, gyroscopes, and accelerometers that track movement and orientation. Vision and camera sensors use various imaging technologies to provide visual perception capabilities for object recognition and navigation. Proximity and range sensors, such as ultrasonic, infrared, and laser sensors, detect nearby objects and measure distances accurately. Force and tactile sensors enable robots to sense pressure, torque, and physical contact for delicate manipulation tasks. Key applications of these sensors include object detection and recognition for identifying items in the workspace, navigation and path planning for autonomous movement, environmental monitoring for safety and efficiency, force feedback for precise manipulation, and quality control and inspection in manufacturing processes. Actuators are the muscles of robotic systems, converting electrical, pneumatic, or hydraulic energy into mechanical motion. Understanding the three main actuator types is essential for robotics engineers. Electric actuators offer high precision and speed control, making them ideal for applications requiring accurate positioning and smooth operation. They include servo motors, stepper motors, and direct current motors. Pneumatic actuators provide fast response using compressed air and are commonly used in pick-and-place operations where speed is more important than precision. Hydraulic actuators deliver high force and power for heavy-duty applications such as construction robots and large industrial manipulators. Key applications include robotic joint movement and positioning for articulated arms and mobile robots, gripper operation and force control for handling various objects safely, linear and rotary motion systems for different types of movement, assembly line automation for manufacturing processes, and precision manufacturing tasks that require accurate and repeatable motion. Feedback control is fundamental to robotic systems, ensuring that robots perform tasks accurately and respond appropriately to changes in their environment. Closed-loop control systems continuously monitor the robot's performance and make corrections as needed. The control loop begins with a reference input that defines the desired behavior or position. The controller processes this input and sends commands to the robot system. The robot system executes the commands through its actuators and sensors. Sensor feedback provides information about the actual performance back to the controller, creating a continuous loop. Three main control strategies are commonly used in robotics: Proportional integral derivative, or PID control, combines proportional, integral, and derivative responses to minimize error and maintain stability. State space control uses modern control theory approaches for complex multi-input, multi-output systems. Adaptive control features self-tuning parameters that automatically adjust to changing conditions and uncertainties in the system. Safety is paramount in robotics, especially in industrial environments where robots work alongside humans. Several key safety standards govern robotic systems worldwide. ISO 10218-1 and -2 define industrial robot safety requirements, covering both the robot manufacturer's responsibilities and the system integrator's obligations. ISO TS 15066 provides specific guidance for collaborative robotics, establishing safety requirements for robots designed to work directly with humans. ANSI RIAR 15.06 represents the American Robot Safety Standards, providing comprehensive guidelines for robot installation, maintenance, and operation. Essential safety measures include physical barriers and light curtains that prevent unauthorized access to dangerous areas, emergency stop systems that can immediately halt robot operation in case of emergency, comprehensive risk assessment, and hazard analysis before system deployment, personnel training and certification programs to ensure proper operation, and regular safety audits and maintenance procedures to maintain safe operating conditions. Proper maintenance is crucial for ensuring reliable robot operation and preventing costly downtime. A structured maintenance schedule helps identify and address issues before they become major problems. Daily maintenance includes visual inspection of all components for wear or damage, cleaning of sensors and mechanical parts to ensure proper function, and battery checks for mobile robots or backup power systems. Monthly maintenance involves lubrication of moving parts according to manufacturer specifications, thorough cable inspection for signs of wear or damage, and calibration of sensors and actuators to maintain accuracy. Annual maintenance requires complete system overhaul, including replacement of wear items and comprehensive testing of all subsystems. Common issues that robotics engineers encounter include sensor calibration drift, where sensors gradually lose accuracy over time, motor encoder failures that can cause positioning errors, worn mechanical components, such as bearings and gears that affect precision, software timing errors that can cause coordination problems between subsystems, and power supply fluctuations that can lead to erratic behavior or system failures. Artificial intelligence integration represents the cutting edge of modern robotics, enabling robots to make intelligent decisions and adapt to changing environments. Three key AI technologies are transforming robotics capabilities. Machine learning enables pattern recognition and adaptation, allowing robots to improve their performance through experience and learn from historical data. Computer vision provides visual perception and analysis capabilities, enabling robots to identify objects, navigate complex environments, and perform quality inspection tasks. Natural language processing facilitates human-robot communication, allowing robots to understand voice commands and provide spoken feedback. The integration of AI brings significant benefits to robotic systems. Autonomous decision-making allows robots to operate independently without constant human supervision, making them more efficient and flexible. Predictive maintenance capabilities use AI to analyze sensor data and predict when components are likely to fail, reducing downtime and maintenance costs. Enhanced human-robot collaboration creates safer and more intuitive working relationships between people and machines. Real-time environment adaptation enables robots to respond quickly to unexpected changes or obstacles in their workspace. Improved task efficiency and accuracy result from AI optimization of robot movements and decision-making processes. Robotic automation is transforming industries worldwide, with several key application areas driving growth and innovation. In manufacturing, robots handle assembly lines and production systems with increasing sophistication, performing tasks from simple pick and place operations to complex assembly procedures. Logistics and warehouse automation represents one of the fastest-growing segments, with robots managing inventory, sorting packages, and optimizing distribution processes. Agricultural automation is revolutionizing farming through precision agriculture and crop management, with robots performing planting, harvesting, and monitoring tasks. Current trends shaping the industry include collaborative robots or cobots integration, which focuses on safe human-robot interaction in shared workspaces. Plug and produce automation systems are becoming more popular, allowing for rapid deployment and reconfiguration of robotic systems. AI-driven predictive maintenance is reducing downtime and maintenance costs across all industries. Human-robot collaboration workflows are being refined to maximize the strengths of both humans and machines. Finally, sustainable and energy-efficient robotics are becoming increasingly important as companies focus on reducing their environmental impact while maintaining productivity. Success in robotics interviews requires mastery of several key technical areas and effective communication skills. The fundamental areas you must understand include control systems and feedback mechanisms, which form the foundation of robot behavior and performance. Sensor integration knowledge demonstrates your understanding of how robots perceive and interact with their environment. Artificial intelligence and machine learning concepts are increasingly important as robots become more autonomous and intelligent. Safety standards knowledge shows your commitment to responsible engineering practices. Understanding industry trends demonstrates your awareness of where the field is heading and your ability to contribute to future developments. To succeed in your robotics interview, follow these essential tips. Understand both theoretical concepts and practical applications, showing that you can bridge the gap between academic knowledge and real-world implementation. Stay current with industry developments by reading technical journals, attending conferences, and following leading robotics companies. Practice explaining complex concepts in simple terms, as this demonstrates deep understanding and good communication skills. Prepare real-world project examples that showcase your problem-solving abilities and technical skills. Finally, demonstrate your systematic problem-solving approach by walking through how you would tackle unknown challenges. Good luck with your robotics, interview preparation, and remember that passion for the field combined with solid technical knowledge will set you apart from other candidates.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.